Let's see where I want to get you all. Oh, further than that. All right, now we're going to start using shortcuts to find derivatives. The differentiation rules are for the sum, the difference, the product, and quotient. And powers, and constant multiples, and so on and so forth. First off, the derivative of a constant function. We have a function, f of x equals some number, say 3. The derivative of that function would be what? Because up until now, how have we defined the derivative? Up until now, we've defined the derivative as the limit as h goes to 0 of our difference quotient. If we did this, if we did that, x plus h would still be 3. So the limit as h approaches 0 of f of x plus is 3 minus 3 over h, which is 0 over h, which is 0. So the derivative of a constant now, can you tell me why it equals 0? Why does the derivative of a constant equal 0? What does a derivative find? What does a derivative find? The what? A difference of what? The derivative finds the slope of the curve at any given point. Actually, the slope of the line tangent to a curve at any one point. That's what the derivative finds. So what's the slope of a constant function? The graph of a constant function is a horizontal line. The slope of a horizontal line is 0. We've also discussed equations like this. The derivative of 1 over x would be what? We did this negative 1 over x squared. Very good. Because I'm going to show you why. Last time we did this using the difference quotient and limit. I'm going to show you once we introduce the concepts of these functions. Um, derivative of a square root of x. So here's the first one. Derivative of a positive integer power. So x to the power n. The derivative of the power function. Bring the power down and subtract 1 from the exponent. So that's the power rule there. That's, look at the top, it's algebra. Don't use those. Those are algebra. Look at the very top.
Oh.
So this is the shortcut from now on. Whenever you have an exponent, just bring the exponent down in front, subtract by 1. Let's look at example 1. A is x to the power 3. What's the derivative? Three x squared. Yeah, because you bring the power down and subtract by 1. X to the power 2 over 3. Bring the power down. So
Two-thirds x.
what's that?
2/3 x to the negative 1/3.
Very good. Very good. Because 2/3 minus 1, which is 3 over 3, becomes negative 1/3. So the way this one would look would be 2 over 3 x to the power 1/3. Very good.
Wait, so which one's the correct way to do it?
Well, I think the computer will take this, but common convention of mathematics is you never want to have a negative exponent. It
Okay.
also says you never want to have a radical on the bottom, because what that one really means, it's a cube root of x. But since our question started with exponents, we end our answer with exponents. And I'm pretty sure the computer will take both of those answers. X to the power square root of 2. The derivative.
So it'd be square root 2x or square root 2 then x.
So, yeah, bring the power down and then subtract 1. One,
Is the x included in the square root or no?
no.
Okay.
It's just square root of 2 times x.
Okay.
Yeah, that's a common mistake a lot of students make, is where does this radical thing end? And if they're right too close, then it looks like it's integrated into it. No, it's radical two times x to the power radical two minus one. One over x to the fourth. The first thing you have to do here is rewrite the equation. We can rewrite this algebraically by saying it's one or x to the negative fourth. Because in algebra, all a negative exponent does is change the location of it. So now we can take the derivative of it. And since our original equation only had positive exponents, then our final answer would be that. X to the power negative four thirds. Bring the power down. And subtract one, which is 3 over 3, which would make it negative 7 over 3. This requires remembering the rules in algebra. How can you rewrite the radical? Remember, in algebra, you can get rid of a radical by making it a rational exponent. Since that one's an invisible two, it's the power 1/2. Distribute the negative, that 1/2 to both of those, we get 2 times 1/2 plus pi times 1/2. 1 plus pi over 2. So that's just rewriting this equation. We haven't taken the derivative yet. Bring the exponent down. Pi over 2 minus 1. The ones cancel. Remember, since we started off with radicals, we have to end with radicals. since the two, because of this rule here, since the two's on the bottom, that's a square root of x to the pi power. That's your answer. All right, let's look at constant multiples. So if our function had some constant times x to some power, or some function of x, the derivative, take the constant out and take the derivative of x to the power n. So it's c times n x n minus 1. That's just if we have a base value of x. What if it's an equation down there? What if instead of just c times x, it's a function of x? We have a constant in front of some function of x. The derivative, again, take the constant out, take the derivative of that function times the constant. Because this u of x, some function of x. Example 2. Take the derivative of 3x squared. Since the 3 has nothing really to do with it yet, we're taking the derivative of x squared. The derivative of x squared is 2x.
Can you do an example of the one you were just explaining, the function of x? Or is that what example 2 was supposed to be?
Like this, like that, yeah.
Okay.
Because I can't say that u of x equals something like 5x squared plus 6x plus 2 is to raise to some power, because we haven't talked about that yet. We'll get to
Okay.
that shortly. If you have a negative inside there, factor out the negative, treat the negative like a constant multiple and take it out in front. Rule. Derivative of the sum rule. where u and v are functions of x. What that means is you could, if you're adding and subtracting numbers, an equation, you can take the derivative of each one of those separately. Here's the example for that. Y equals x cubed, 4/3 x squared, minus 5x plus 1. Find y prime.
You said you find the derivative of each individual.
Right. Do the derivative, since it's all the sum and difference, just do each one of those individually. So the derivative of x cubed is 3x squared. The derivative of 4/3 x squared. Leave the constant alone, bring the 2 down, 2x. Oh, we're gonna talk about this really quick. The derivative of x is 1. Can anybody guess why it's 1? We haven't talked about it yet, so you can't find it anywhere. Just using what you know of math. What's that? Kind of. Because what's the exponent of x? Using the power rule, you bring the 1 down and subtract 1. X to the 0 is 1, so it's 1. So the derivative of 5x would be 5. And the derivative of a constant is 0. Three x squared plus 8x over 3 minus 5. That's the derivative of that function. Example 4. X to the 4th minus 2x squared plus 2. It says, does the curve have any horizontal tangent lines? If so, where? So how do you think we'd find this? It depends on, it all bases itself on the definition of a derivative.
Is that could we use derivatives, or is that not the right way?
Well, we have to. How do we find a horizontal tangent line? How do we know it's horizontal? The slope of a horizontal line is 0, right? So how do we find the slope of this function? Find the first derivative. Since we learned shortcuts, we find the derivative of this, which would give us 4x cubed minus 4x. So what we have to do now is set this equal to 0. And solve for x. Factor out of 4x out of both of those. This is a difference of two squares. So my zeros are where? Nope. It's not the answer. You're close, but not the answer. How many answers are we supposed to get? How many do we have? How many factors do we have? So what do you do with each factor? What about that one? 0. So there's x is 0, x is -1, and x is 1. So the curve x to the fourth has horizontal lines at x equals 0, x equals 1, and x equals -1. Okay, let's see if you guys go a little further in your math skills. What happens at these points? What do we find there? If we were going to graph this function, what will these find for us? No. Because to find the x-intercepts, we have to set this one equal to 0. And we know it's not going to be equal to 0 because there's no way it could work. Not the y-intercept. The y-intercept is 2.
It's where it turns, or not turns,
I know what you're trying to say, but see if you get the right words out.
was it crosses your white? No.
No. Remember, let's look at this. Horizontal tangent lines. So we have the function x to the fourth, 2x squared plus 2. So if we plugged in 0, -1, and 1 in there, we get the y-intercept, or the y-intercept is there. We get 1 minus 2. We get 1. So if we graphed this one, we have at 0, it's 2. At -1 and +1. What kind of shape is it going to have? What's the end behavior of the graph look like?
Parabola.
It's like a parabola. Yeah. So in other words, both ends point the same direction. Since it's positive, they both point up from the last points. What we've just labored to produce are the vertices. Each vertex has a slope 0. You guys were right, but it wasn't what I was looking for. Derivatives of exponential functions. What does an exponential function look like? What is it? What's the form of an exponential function? That's an exponential function. So the derivative of an exponential function typically the function we'll use more so in this class is, we'll say EU. Whenever you have an exponential function, because there's no x down here. So the derivative is the function itself times the derivative of your exponent. So in our case, it'll be EU du. So if I gave you the function e to the 3x cubed, what would the derivative be? So what this formula here says is leave the function alone. And what's the derivative of the exponent?
It's multiplied times 3.
Squared. Yeah, so there's your derivative. So yeah, exponential equations are pretty quick and easy to do. Let's look at example 5. It says find the equation of the line tangent to y equals ex going through the origin. Find the equation of the line tangent to the graph of e to the power x going through the origin. So to find an equation of a line, we need two things. We need a point and we need a slope. Do we have either of those? Can we find either of them? So this is what it's really saying. It wants an equation of a line tangent to this graph going through the origin. So it wants the equation of that line.
Should we plug in numbers?
What number are you gonna plug in?
I meant like, what do we do, like the -1, 0, 1?
No, you wouldn't need to. Where's the origin? 0, 0. How do we find the slope? The slope is the first derivative. So the first derivative of our function is e to the power x is e to the power x. The only point we know is 0, 0. So if we plug in 0 there, our slope is 1. But we know the y-intercept already. It's going through 0, 0. So that's gone. The slope is 1. So tangent to the curve, it's at some point A, it'll have that slope. So get products and quotients. Now we're gonna get a little bit more application, not application, but process driven. So here, the first one we're gonna talk about is the product rule. So we have two functions. F of x times g of x. Let's say that equals h of x. To find the derivative of h of x. Okay, I'm going to show you a shortcut that will work for both the quotient and the product rule. Call it the fishy rule. All right, so here are two functions, f and g. Find the derivatives of both of those. Since we will start in the first quadrant and we'll make a fish. Since we're dealing with, when you multiply things, you make them bigger. So we're going to use the plus sign between them. It's going to be g of x times f prime of x. Let's multiply these two together. Add f times g prime. So whatever your f and g, f prime, g prime, and do a little fishy thing. The quotient rule here we're looking at if f of x divided by g of x but when you divide things, you make them smaller, right? So in the quotient rule, we'll use a minus sign instead of a plus sign. And that's going to be the top. So it's g of x times f prime of x minus f of x g prime of x. Divided by the square of your denominator. It'll memorize these little fishy things. So if it's a product, you're making things bigger, it's a plus. If it's a quotient, you make things smaller, use a minus. All right, let's look at an example here. Actually, I'm gonna give you a smaller one first. F of x equals x to the third, and g of x equals e to the 2x. H of x equals f times g, and h of x equals f divided by g. Find h prime. So the first thing you have to do is do your F and G, F prime, G prime. So F of X is X cubed. What's F prime of X?
3x squared.
3x squared. And G of X is e to the power 2x. So G prime would be we know it has to be that. What's the derivative of 2x?
So does the 2 just get put in front?
Yeah. And it goes in front.
Is that because it's not like the example we did, e to the power of 3x squared?
What's that again?
The example that we did earlier was e to the power of 3x squared.
Yes. Oh, yeah, yeah. I should have put the 3x squared out in front or the 6x, yes. Because you usually won't always have the x term in the back. Yes, you're absolutely correct. So use the fishy thingy for the product. We add them. So it's G times F prime plus F times G prime. Three x squared e to the power 2x plus 2x cubed e to the power 2x. And if you want to, you can factor out the two e to the 2x. So both of these answers would work. So that's the product rule. Now the quotient rule, we use the same functions, except here we subtract. Gf prime minus fg prime over g squared. Minus. Two x. And there's your derivative.
So even though for the first one, even though we're just multiplying by each other, they just end up more or less adding together.
Yep.
Okay.
Because you're multiplying two functions and each part of the function has to be taken in individually. That's why you add them together.
No, I meant like, so like e to the power of 2x is multiplied by 3x squared. That just comes out to be 3x squared e to the power of 2x. That is, it was just basically adding them together.
Yeah, combine it, yeah. It's using the commutative property. I can move them around however I want to make it look nicer. All right. Let's look at example 6. Find the derivatives of y equals 1 over x squared plus e to the x, and y equals e to the power 2x. There is no wrong way you could do. You can make this as a product rule, or you can distribute that and simplify this one and have a quotient over here. So you use whatever is easiest to you. Well, this would be f, this would be g, and we do the derivative of this, we have to do the sum rule. Or if you wanted to, you can distribute both of them out. We have x squared over x plus e to the x over x. And this is still our original. X squared over x is simply x. The derivative of x is what? One. Now we're going to do derivative of this one. We have e to the x times x, e to the x times 1. This is f g f prime g prime. So we're going to have x e to the x minus 1 times e to the x. Which could be written as 1 plus x minus 1 over x squared e to the x. Again, or you could have done both of them separately as a product rule. The derivative of the next one. What's the derivative of e to the power 2x?
2e to the power of 2x.
Exactly. Good job. Just leave the e, leave it alone and take the derivative of the top. All right, so let's look at example 7. It's a quotient rule. y is equal to x squared minus 1 over x cubed plus 1. And b, y is equal to e to the power negative x. The top is our f, the bottom is our g. So we have to do the f, g, f prime, g prime. So f is x squared minus 1. G is x cubed plus 1. So the derivative of the numerator is what? 2x. Just subtract 1. And g is 3x squared. Since it's a quotient, we subtract. So y prime is g, which is x cubed plus 1 times 2x minus x squared minus 1 times 3x squared. All over the denominator squared. Two x times x cubed is 2x to the fourth plus 2x minus 3x squared, it's 3x to the fourth minus 3x squared. Distribute the negative. 2x to the fourth plus 2x minus 3x to the fourth plus 3x squared. Combine like terms. 2x minus 3x is negative x to the fourth plus 3x squared plus 2x x cubed plus 1 squared. That's your derivative.
We should not factor out that at all from the beginning.
Well, you couldn't, because if you took out an x, then you have x cubed plus 3x plus 2. So it'd be a cubic function. No, I just leave it as that, because only thing you could do left is if I give you a value for x, let's say 2, plug it in there. Unless it's obvious and straightforward that the numerator will become something like the bottom. But other than that, no, don't waste your time with it. The next one, the derivative of this one. We know it has to be e to the power negative x. The derivative of negative x is -1. So it's negative e to the power negative x. So far, so good. Okay, let's combine a lot of these rules. Y is equal to x minus 1, x squared minus 2x over x to the fourth. Now, how many of y'all would use the quotient rule and the product rule here? Good. You could do that where this would be F and this would be G. When you take the F prime, you have to do the product rule. Or you can multiply them together, which would be the best thing to do so far. If we multiply these two together, we get x cubed minus 2x squared minus x squared plus 2x over x to the fourth. Combine like terms. Negative 2x minus x squared makes it negative 3x squared all over x to the fourth. Now, since you have a monomial on the bottom, divide each one by that denominator. So our original equation now becomes this. Now we just take the derivative of each one of these separately. You don't have to use the quotient rule either. Oop, this is. All I did is multiply the two top numbers together and then divide by the denominator. I can rewrite each one of those as negative exponents. This will make finding the derivative a lot easier. So bring the exponent down, subtract by 1, I get negative 1 x to the power negative 2. Three, bring power down and subtract 1, I get negative 3. And subtract 1 from the top. Rewrite them with positive exponents. And there's your derivative.
So why on this one did we combine the top? But on the,
Because we have
but on the one
a monomial
before-
on the bottom, it's much easier if we had just one equation on top. That way we could take that denominator and put it under each one separately. If the bottom was a binomial or a trinomial, then we would use something else.
Okay.
But since we had two binomials on top, we could combine them and get a trinomial. That way it'd be easier to take a derivative of it. Because taking the derivative of, if we're doing the quotient rule, derivative of this one's a lot easier than having to do the product rule here and get the same answer. So yeah, it's just, it's saying is there's no right way, no wrong way. It's just that whatever way you see is easiest for you, that'll save you from having to write a million things. Higher order derivatives. So far, all we've been doing is taking the first derivative. Plus, let me do y is equal to x cubed minus 3x squared plus 2. Let's find as many derivatives as we can. So what's the first derivative going to be? You do each of these separately. The derivative of x cubed is
3x squared
3x squared
minus 6x and
minus 6x. The derivative of 2, 0. Second derivative. Derivative of 3x squared is 6x. The derivative of 6x remember, the derivative of x.
is it 6x or negative 6x that we're looking for?
Well, for this first part,
No. Sorry, I got the 3x squared minus 6x, but are we looking for the derivative of negative 6x or just
no, we're
positive?
looking at the derivative of the whole equation. The 3x squared minus 6x, the whole thing. So the derivative of the 3x squared is 6x. The derivative of negative 6x is negative 6. So the derivative of this equation six, because yeah, the derivative of 6x is 6. The derivative of 6 is 0. And the fourth derivative, 0. A good question. The question was, what is the point of finding higher order derivatives? In physics, the position function is denoted by S of t. That's the position you are anywhere in space and time. Or we also speed, velocity, or what we refer to as speed, is the change of that position over time. So it's the first derivative of that. Acceleration is the first derivative of velocity which makes it the second derivative of your position function. The jerk is the first derivative of your acceleration, which is the second derivative of your velocity, which is the third derivative of your position. So each one of them finds a different rate of change of a different function. Yeah, a lot of people never heard of jerk. They just usually just call jerk.
I mean, that's what I assume.
Yeah. Because if you're accelerating, it's one little faster jerk. That's what it happens instantaneously. Each one of these are instantaneous rates of change. Well, let's